In this video, we're going to talk about what happens when we mix acids and bases when one of either the acid or the base is a weak acid or a weak base. So if we mix a strong acid and a strong base, that case allows us to form just water and some salt that's going to be dissolved in our water, so we would have a pH around 7. But our calculations are a little bit more involved when either the acid or the base is weak. So let's look at a scenario, or a few scenarios here, where we have either a weak acid or a weak base. So when we added sodium hydroxide to our hydrochloric acid, we saw that there was a sharp increase in our pH, and in the middle of that was our equivalence point. Well, if we have acetic acid, we have something similar happen, that we have a sharp increase in our pH, and halfway through that is our equivalence point. But what you'll notice is the equivalence point is higher than the equivalence point when we had hydrochloric acid. So the products of this reaction are water and sodium chloride, which is going to be aqueous, that's going to be dissolved in our water. So sodium chloride isn't really going to affect the pH, so we're essentially taking the pH of water, which is pH of 7. But when we have acetic acid here, our base is much stronger than our acid, so we're going to have a pH that's more of a basic pH. So we have a pH of about 8.73. So in the basic range, since our hydroxide is going to affect the pH. So let's look at some calculations. In this case, we're going to look at a weak acid and a strong base. So we first want to know what volume of titrant is required to reach the endpoint. So our titrant is our 0.1 mole of sodium hydroxide. So when we do titrations, we always start with the one that we know everything about. We know the volume and we know the concentration. And let's go ahead and write our reaction up here at the top. So we have acetic acid, and that reacts with, we don't really care about the sodium, we only care about the hydroxide ion. So we're going to get acetate out of that. More precisely, we're going to get sodium acetate, but like I said, we don't really care about the sodium because it doesn't affect the pH. We only care about the acetic acid and the hydroxide ion. And we're going to get water. So we want to react 25 milliliters of 0.5 molar acetic acid with 0.1 molar sodium hydroxide. So if we take our 25 milliliters of acetic acid, and there are 1,000 milliliters of acetic acid per liter of acetic acid, and then we're told that we have 0.5 molar, so that means that 1 liter of acetic acid has 0.5 moles of acetic acid in it. So I'm out of room, so I'm going to have to put the rest of my calculation on the next line here. So we have, according to our reaction, 1 mole of acetic acid reacts with 1 mole of sodium hydroxide. And we have a 0.1 molar solution of sodium hydroxide. So 0.100 moles of sodium hydroxide per 1 liter of sodium hydroxide. So if we take 25 times 0.5 and then we divide that by 1,000 times 0.1, we get 0.125 liters of sodium hydroxide. Or if we convert that to milliliters, that would be 125 milliliters of sodium hydroxide. So this time, we don't know what the pH is. So we need to figure out a way to calculate the pH of this. Since we're reacting a strong base, we won't know what the exact pH is. So we need a way to figure out what the concentration of our hydroxide is here. So at equilibrium, when we've reached the equivalence point here, we have our acetate ion floating around in solution. And that's reacting with water. So that's going to give us our acetic acid and some of the hydroxide ion. So we can figure out the concentration of the acetate ion. We started with 0.025 liters if we convert the 25 milliliters to liters. And we have 0.5 molar. So if we multiply that together, 0.025 liters times 0.5 molar, we have 0.0125 moles of the acetate ion. Now we calculated that we had to add 125 milliliters of sodium hydroxide, and we started with 25 milliliters of the acetic acid. So if we take our 25 milliliters and we add the 125 milliliters that we added, we now have 150 milliliters of solution here. So if we take 0.0125 moles and we divide that by 150 milliliters is 0.150 liters. So we divide that by 0.150 liters. That gives us 0.0833 molar. So this is the concentration of our acetate ion. But we want to know the concentration of hydroxide. So we're going to make an ice table and determine what our concentration of our hydroxide ion is. So we have CH3COO negative, which is our acetate ion. We have our acetic acid. And then we have hydroxide. So we have our initial concentration of acetate, we calculated was 0.0833 molar. And initially, we wouldn't have any acetic acid or any hydroxide. So over the course of this reaction, our acetic acid concentration is going to decrease and our acetate concentration is going to decrease. Our acetic acid and our hydroxide ions are going to increase. So we have 0.0833 minus X, and X for our hydroxide and our acetic acid concentrations. So, since this is a base here, our acetate ion, we can write a Kb expression for this reaction. So Kb is equal to the concentration of acetic acid times the concentration of our hydroxide ion over the concentration of our acetate. So we know what the pKa is, and we need to use that to calculate Ka. And then once we do that, we can use that to calculate Kb. So pKa is given to us as 4.74, and pKa is equal to the negative log of Ka. So 4.74 is equal to the negative log of Ka. And the way that we get rid of a log, first we want to get the log by itself, so we have 4.74 equals the log of Ka. And then we want to get Ka by itself, so Ka is equal to 10 to the negative 4.74, which comes out to 1.82 times 10 to the negative fifth. Now we want to know what Kb is, so we can use the relationship between Kb and Ka to get Kb by itself. So Kb is equal to Kw over Ka, and Kw is 1 times 10 to the negative 14th. If we divide that by what we calculated for for Ka, then we'll get Kb, which is 5.495 times 10 to the negative fifth. So I'm purposefully keeping a few extra decimal places here because we don't want to round off too early and cause that to cause errors in our final answer. So we run our expression for Kb. Now that we have Kb, we can plug that in. So we have 5.495 times 10 to the negative fifth. Our concentration of acetate and hydroxide is X, and our concentration of acetate is 0.833 minus X. Now to make our life simpler, we're going to assume that the X down here is so small we can consider it to be 0. Now this only works if X comes out to be less than 5% of our initial concentration, but we can make the assumption and see if that holds true at the end. So if we take 5.495 times 10 to the negative fifth, times 0.0833, we get, so X times X is X squared, and if we multiply these two together, we get 4.58 times 10 to the negative 11th. So if we take the square root of both sides, X is equal to 6.77 times 10 to the negative 6. And since we called the hydroxide ion concentration X, this is also the hydroxide ion concentration. So we get 6.77 times 10 to the negative 6 molar. Now what we can do is calculate the pOH and then subtract that from 14 to get the pH. So I'm going to come back up here. So pOH is going to be equal to the negative log of our OH concentration, which is 6.77 times 10 to the negative 6 molar. So if you put that into your calculator, negative log of 6.77 times 10 to the negative 6, that gives us 5.17. So pH is equal to 14 minus the pOH, which is 14 minus 5.17. So we get 14 minus 5.17 comes out to 8.83. So that's going to be the pH of our solution where we added acetic acid and sodium hydroxide together. Now, if we go the opposite direction, we add a strong acid to a weak base, we're actually going to decrease our pH. So if we start with something like 0.1 molar ammonia, we have a pH here of about 11.12. As we add hydrochloric acid to this, we eventually get to a point where we're at the equivalence point, and then if we keep going, we decrease the concentration. So we decrease the pH, and we get to a point where we have more acid than we do base here. So we're still in, as we're adding hydrochloric acid initially, we're still in a region where we have more ammonia than we do hydrochloric acid here, and we're in what we call the buffer region. We've added enough hydrochloric acid that we shift some of this equilibrium towards forming the ammonium ion, so we call this the buffer region here. Eventually we get to a point where we've added enough hydrochloric acid that the number of moles of hydrochloric acid is equal to the number of moles of ammonia, but we're going to have a pH less than 7 since the hydrochloric acid is stronger. And then if we keep adding, we get to a point where we have excess H2O+. So let's look at a calculation where we have a weak base, which is ammonia, and we're adding that to hydrochloric acid. So if we write out the reaction for this, we have NH3 plus hydrochloric acid gives us NH4Cl, so ammonium chloride. So first we want to know what volume of titrant will be required to reach the endpoint. So this is a calculation that we've done a few times here, so we can go ahead and set this up. We have 40.0 milliliters of ammonia, and we want to convert that to liters. So we have 1,000 milliliters of ammonia per 1 liter of ammonia. And I'm going to write this a little bit smaller here, so that I have enough room. And then, according to our reaction here, 1 mole of ammonia reacts with 1 mole of hydrochloric acid, and then we have a 0.1 molar solution of hydrochloric acid, which means that we have 0.1 moles of hydrochloric acid per 1 liter of hydrochloric acid. So we have, if we do the multiplication here, 40 times 0.1, divide that by 1,000 times 0.1, we get 0.04 liters of hydrochloric acid, or 40 milliliters of hydrochloric acid. So then we want to know what the pH of this is at the end point. So at the end point, we don't really care about the chloride because that doesn't affect our pH. So ammonium chloride would give us ammonium ions and chlorine ions. But all we really care about is the ammonium ions. So this is aqueous, which means that our ammonium ions are in water. And that's going to give us ammonia and H3O+. So we need to know what the concentration of ammonium ions is at the end of this. So we started with 40 milliliters of our ammonia, and then we added 40 milliliters of hydrochloric acid to it. So that gives us a total of 80 milliliters, which is 0.080 liters. So we want to know how many moles of ammonia there were, and that will give us the moles of ammonium ions. So if we take 40 milliliters and we convert that to liters, that's 0.04 liters. So we have 0.040 liters of ammonia. And we start with 0.1 molar ammonia. So 1 liter has 0.1 moles in it. So 0.04 liters times 0.1 gives us 0.004 moles. So we take 0.004 moles, divide it by the number of liters. So that gives us a concentration of 0.05 molar. So this is the concentration of our ammonium ions. Now to calculate pH, we need to know the concentration of H3O+. So we're going to take our ice table here. We know the concentration of ammonium ions, so we can use that to calculate the concentration of ammonia and H3O+ at equilibrium. And what we're really interested in is the H3O+, because that will get us what we need to calculate pH. So we came up with a concentration of 0.05 molar for our ammonium ions. And at equilibrium, we have a concentration of NH3 and H3O+. So over the course of this reaction, the concentration of NH4 positive is going to decrease, and the concentration of our ammonia and H3O+ is going to increase. So we're going to have 0.05 minus X for our concentration of ammonium at equilibrium, and we're going to have X for the concentration of NH3 and H3O+. So we need to know, since we're forming an acid here, our Ka. So we need to write an expression for Ka, so that's going to be NH3 times H3O+ over NH4. Now we were given pKb, and we need Ka. So we're going to have to do some calculations here and calculate our Ka. So pKb is equal to the negative log of Kb So 4.74 is the pKb that we were given. So that's equal to the negative log of Kb. So negative 4.74 would equal the log of Kb. And the way we get rid of the log is that we take 10 to the power of whatever we have. So Kb is 10 to the negative 4.74. So if we work that out, we again get 1.82 times 10 to the negative fifth. So we need Ka. So Ka is Kw over Kb. So we take 1 times 10 to the negative 14th divided by 10 to the negative fifth. So that gives us 5.49 times 10 to the negative 10th. So if we plug this into our expression for Ka, we have 5.49 times 10 to the negative 10th is equal to the concentration of ammonia in H3O plus, we represented as X, and our ammonia is 0.05 minus X. So we're again going to assume, to make our lives a little bit simpler here, that X is so small that it's negligible. And we can check that at the end and make sure that that assumption holds true. So 5.49 times 10 to the negative 10th times 0.05 gives us 2.75 times 10 to the negative 11, and that is equal to X squared. So if we take the square root of 2.75 times 10 to the negative 11, we get 5.24 times 10 to the negative 6th. So since this is what we represented H0 plus as, we represented H0 plus as X. X is also the concentration of H0 plus. So now that we have the concentration of H0 plus, we can take pH is equal to the negative log of H0 plus. So that's the negative log of 5.24 times 10 to the negative 6. If you plug that into your calculator, you should get a pH of 5.28 for the solution. So since our acid is stronger than our base, our pH should be in the acidic range. And we did come up with a pH in the acidic range. So we will stop here and we will look at some more examples of this and do some calculations in class. So I will see you in class.